All right, welcome. Ever wondered how we take that simple idea of a tangent line and just kind of launch it into the third dimension? Well, you're in exactly the right place. Today, we're going to demystify one of the biggest concepts in multivariable calculus, the tangent plane. Let's get into it. So you definitely remember from Calc 1 how a tangent line is the best possible straight line approximation for a curve at one specific point, right? Okay, well, just think of a tangent plane as its bigger, way more impressive sibling. We're leveling up from a 2D curve to a 3D surface, so it just makes sense that we'd need a flat plane to approximate it instead of a tiny little line. It's the same exact idea, just with another dimension. So here's our game plan. We'll start by making that jump from lines to planes super clear. Then we'll nail down what a tangent plane actually is. After that, we're going to break down the formula so it's not intimidating at all. We'll walk through a real example, see its power in action with an approximation, and then wrap up with the one thing you absolutely need to remember.
As we get going, just keep this one thing in the back of your mind. Going from a 2D tangent line to a 3D tangent plane, it's not some crazy, impossible leap. It's actually a really intuitive, logical next step based on stuff you already know.
Okay, so what exactly is this thing we're trying to find? Let's get a really sharp definition, and more importantly, let's visualize what this tangent plane is even doing.
So here's the deal. A tangent plane is basically a flat sheet of paper that just kisses our curvy 3D surface at one single point. But, and this is the important part, it's not just any old plane. It has to be tilted just right, perfectly matching the steepness of the surface at that point, and not just in one direction, but in both the x and the y directions at the same time. All right, here it comes, the part that sometimes looks a little scary, the formula. But I promise you, once we pull it apart, you're going to see it's built on a foundation you already totally understand. And that's the big question, right? A picture is great, but this is calculus. We need an equation we can actually work with. So how do we capture that perfectly tilted, slope-matching plane with some algebra? Let's rewind for just a second. Everybody remembers good old point-slope form for a line, right? You get a point, you get a slope m, and bam, you can define the entire line. It's simple, it's elegant, and it works. And here is the absolute best part. The tangent plane formula isn't some crazy new thing you have to memorize from scratch. Nope, it's a direct, totally logical extension of the point-slope form we just saw. We're just adding in that z-axis. And there it is. Yeah, it looks a little longer, but check out the similarities. We still have our point, it's just x naught, y naught, z naught now. But instead of one slope m, we've got two. We have fx, that's the partial derivative with respect to x, which is just the slope in the x direction. And we have fy, the partial derivative with respect to y, you guessed it, that's the slope in the y direction. Seeing them side by side like this, it makes everything click. On the left, our old friend, the 2D formula. Notice how y is the output. Now look to the right. In our 3D world, z just takes the place of y. And where we used to have a single slope, m, well, now we have two separate slopes. Fx tells us how steep it is when we move along x, and fy tells us how steep it is when we move along y. It's the same skeleton, just, beefed up for 3D. Theory is one thing, but let's make this real. Let's jump into a worked example and see exactly how to use this formula, step by step. The process is pretty much always the same, and it boils down to 3 easy steps. Let's say we have the function f of x comma y equals x squared plus 4y squared, and we care about the point 2 comma 1. Step 1, find the general slopes by taking the partial derivatives, fx and fy. Step 2, plug in our point 2 comma 1 to get the specific slopes right at that spot. And finally, step 3, we grab our point, our z-value, our two new slopes, and we just plug them all in to build the final equation. So let's do it. The partial with respect to x, fx, is just 2x. At our point, x is 2, so that slope is 4. Easy. The partial with respect to y, fy, is 8y. At our point, y is 1, so that slope is 8. Now we just plug it all into the big formula. Z minus 8 equals 4 times x minus 2, plus 8 times y minus 1. We do a little bit of algebra, clean it up, and we get our beautiful final answer. Z equals 4x plus 8y minus 8. That's it. That's the equation for our plane. So finding the equation is pretty cool. But why do we really care about this? This next part is where the true power of the tangent plane shows up. It's an amazing tool for something called linear approximation. Okay, imagine you get hit with this problem. No calculator. I mean, this looks just awful, right? Those numbers 3.04 and 3.98 are so messy. But what if I told you they're really close to some nice, friendly numbers? This is the perfect job for a tangent plane approximation. So here's the strategy. It's actually genius. First, we find the tangent plane equation, which we can also call the linearization, at a nice, easy point nearby, like 3, 4. Then, we use that super simple plane equation as a stand-in for the messy original function, and we plug our tricky numbers into it. Since our point is so close to where the plane is tangent, the plane's answer should be incredibly close to the real answer. So, after we find that tangent plane at 3, 4 and we plug in our messy numbers, the answer we get is 5.008. That was a pretty clean calculation. But the real question is that any good? How close did we actually get? Just look at this. Our guess was 5.008. The actual value, if you use a calculator, is 5.00819. I mean, come on. That is unbelievably close. The error is basically nothing. Think about what we just did. We used a simple flat plane to estimate the value of a complex curvy function, and we got an answer that was accurate to 3 decimal places. That is the real power of linear approximation, and it's all thanks to the tangent plane. So, as we wrap things up, what are the big ideas you should be walking away with? Let's boil it all down. Okay, here it is. Number 1, tangent planes are just tangent lines but for 3D. Simple as that. 2, they are the absolute best flat approximation you can get for a curved surface near a point. 3, that formula is not scary. It's just the point-slope form you already love, but with 2 slopes for 2 directions. And finally, putting it all together, this idea lets us do incredibly powerful linear approximations for really complicated functions. And I'll just leave you with this little thought to chew on. We just saw how a totally simple flat plane can help us understand a much more complex curved surface. It kind of makes you wonder, doesn't it? What other powerful tricks and elegant simplifications are just hiding in plain sight, waiting for you as you go deeper into calculus?